Hi, my name's Wayne Callan. We're looking at another alternative final sub-circuit arrangement within the M.E.N earthing system on drawing AO1. So if you look at the top of this drawing, we can see that again is the same with drawing A. It's got the three houses that are represented. And the M.E.N three-phase supply distribution protective earthing and the RVT high resistive earthing is the title. So what is high resistive earthing? Well, in international standards it's HRG, which is high resistive grounding, and the ground and the earth mean the same. We just use that term earth in Australia rather than ground. It's made up of three types, as we said before in the previous video, and the TN earthing system is over here. You've got the TNS, the TNC, and the TNCS. With the TNCS is the predominant, which is mandatory for final sub-circuits in commercial, housing, and industrial situations now that you have this earthing system. And we're just going to go through and have a look at it. I developed the RVT after an accident involving a hairdryer in a bath in a brand new house in 1997. What caused the RCD to fail? What caused the RCD to fail was the development of this term here, island mode. It's taken me personally 25 years of research to understand what happened back in 1997. And so hopefully this drawing will help you understand what happened, how island mode evolved, and what caused voltage rise on the protective earth to start being a new phenomenon as well. So the main things that have caused island mode is changes in building codes. Waterproofing in high risk areas such as your bathrooms, your kitchens and your laundries is now a lot more technical. It's totally fiberglass, and it's taken out a lot of the what we call like connection to ground, which is your true earth, which is, you know, your earth stake area. So your concrete, your Rio and everything like that in your concrete on your slabs. Once they put down the wet seal, your bathrooms are now isolated. And changes in plumbing codes, that's another one where you've got copper piping replaced by polybutylene. So copper obviously became too expensive and plastics were a lot cheaper. And galvanized drain pipes, they're now PVC. So they've taken out a lot of the earth points that were in the bathrooms, in the kitchens, you know, in your laundries. And your baths themselves and your showers, you know, they're now fiberglass. So that's what has predominantly caused, and plus the failure in, say, the utilities. Something's happened in the utilities. So the plumbers and the builders took out this connection here as note 7. There's no connection because as I say, the PVC piping, the polybutylene. So over in your bathrooms you don't have any earthing points. Your taps used to be all an earth point, you know, so they're now with the fiberglass piping there, that's gone. So this drawing is actually a true indication of existing houses. So and the RVT, as I said, it just sits, was invented in 97, and it's taken me, you know, 20 something years to get to this point. So it sits beside the RCD. The RCD technically will look for current, and it uses a coil to, you know, check for an imbalance between the active and the neutral. And so the RVT has no reference to ground, it's voltage, so it doesn't need you know, like to have that reference to ground, as I say, to earth. So when you combine the two units together, it gives you a totally increased safety level. So again, as we did before, we just go quickly through the mains. The active goes all the way down through the RCD. None of this changes from the previous video, except that across the top you haven't got the TNC joining of the neutrals, which is at your, say, supply transformer or power pole out the front. You know, that's generally where the join may be made, but it comes down, goes straight down through your consumer neutral, all the way through and down to your final sub-circuit there, your power point. And we just see that the RVT attaches to the pen, the TNC neutral, which is a combined earth and neutral. So we just attach to that there, and then through our electronics we turn that into a high resistive earth point, because we're actually using the pen, the TNC there, back that way. So that's how we get away. We negate having this, although it's illustrated, the earth coming down to here, that's not you know, we leave that in because we're using the same cabling, you know, TPS cable, 2-core and earth, so we're not going to change that. We use the earth inside the TPS cable to run all the way back there to the RVT. So as again, the earth goes down out to true ground, and in house 2 that's the only true earth in the house, whereas in house 1, true ground, you know, you've got all those bathroom points, laundry points, you know, and drainage points, gas piping points, everything like that. Well, over here we don't have any of that at all. So the notes are pretty much the same as in drawing A, and so you've got and obviously we've got the solar's just in the third house, one house in the street type of thing, or every 3 houses, 1 in 3 houses, you know, just to show that what happens when you've got a breakdown, you know, over in house 1, as we went through before. If you lose, say, the M.E.N bond down here, or you lose your neutral link, supply neutral, or reverse polarity, they all have catastrophic effects on the earth going down here all the way over to, you know, this solar up here, which is, you know, that's just the way the TNCS earthing system is evolved. As I say, the join is also across the top through the utilities poles and wires, and so any one of these houses has a problem, then it'll end up there. And so what we could do with the solar is put one of our units on up here, and it would give it you know, protection, and use the same, you know, pen arrangement down here. So you sort of we have looked at that as well in our planning. So thank you for listening.